All right, so good morning. Well, I was told I needed to stand over here because there's a camera, everything, since we're broadcasting, right? All right, good morning, everyone. It's my distinguished pleasure to introduce our speaker for today for our CFCS Distinguished Lecture Series. Yeah, so it will mark the very last one for the semester. So today we have Professor Dinesh Manocha from University of Maryland to talk about the recent work and the challenges regarding robot operations in uncontrolled environments. Let me introduce briefly about Professor Dinesh Manocha, who's a Paul Chrisman Erid Chair in Computer Science and ECE, and a distinguished university professor at the University of Maryland, College Park. His research interests include virtual environments, physically based modeling, and robotics. His group has developed a number of software packages that are standard and licensed to 60 plus commercial vendors. He has published more than 600 papers and supervised 40 PhD dissertations. He's a fellow of AAAI, AAAS, ACM, and IEEE, member of ACM SIGGRAPH Academy, and the Bezier Award from Solid Modeling Association. He received the Distinguished Alumni Award from IIT Delhi and the Distinguished Career in Computer Science Award from Washington Academy of Sciences. He was the co-founder of ImpoSonic, a developer of physics-based audio simulation technologies, which was acquired by Valve Incorporation in November 2016. Professor Manocha has been a frequent visitor to China, and he also made a trip to our center, give a talk a couple of years ago before the pandemic, before a different age of time. So I'm glad that we're having Professor Manocha with us today. I guess he hasn't been sitting there idle during the pandemic for the last 2 years. So I look forward to listening to your recent advances. All right, without further ado, let's welcome Professor Manocha.
Thank you, Bao Chen, for the kind introduction. It's always an honor. I should tell you, I've been to Peking University or Beijing University many times. My first trip was in 2007. I still remember. I come to both Peking University and Tsinghua very often, and Chinese Academy of Sciences. And I have a lot of collaborators, at Peking University. One of them is a computergraphy professor, Li Shang and Goping Wong. And of course, I have the pleasure of knowing Bao Chen for more than 20 years. I was in his building in 2019 when I was visiting, this thing there. So this is the project. We have a large group at Maryland on robotics, and we have some really big projects going on here. But the work I'm presenting, I was at University of North Carolina, Chapel Hill till 2018. Some of the projects go back to 2018. A lot of my students from UNC Chapel Hill. I also have a lot of students at Maryland, a lot of the work I present. But I also have a strong collaboration with Baidu Research. Their big office, of course, is in Beijing. I've been there, but I've been working with my former student, Liangjun Zhang, who heads the robotics and automation lab there. And before that, it was Ruigang Yang, who was there. So in fact, you'll see I'll present one of the big projects, which is on robot construction, and that is mostly done with Baidu Research. And also I'm working autonomous driving. It's a very hot topic in industry. I have a lot of collaboration with a lot of industry players, again, Baidu and Intel, and even Waymo and other players. These are very expensive projects. So this is what I'm presenting work is a collaboration with lots of people on my campuses, but also in industry. And the focus here is, how is robotics coming along and where the challenges are there. So robotics field is, at least 50 years old. The first commercial robots were deployed in 1960s in US in automobile industry, so we are 2022 now, so it's more than 65 years old. And the first robot that were deployed, they were for tasks like welding, painting, and assembly. They were just programmed to do a task. It's like, you record a music in your iPhone, and you play the music. It's just same signal, MP3 files plays. So they have been used for a long time for just tasks, just same repetitive tasks, just doing like a manual work. Then we saw a lot of focus in 90s and 80s on medical robotics, where robots are used in medical devices for surgery, surgeon controlling them. And if you look at the last 20 years, there have been a lot of consumer robots. Sony came with Abo off and on. So there have been robot products, but they had limited success. So robotics has been around, but till 10 years ago, there was very little success behind some industry. Now, this is a lot of exciting time. We are like, at least in media, it's the same in US and maybe the China. A lot of hype on AI, robotics, and autonomy. There's a lot of excitement. Perhaps hype is always higher. When you see some robot, a couple of months ago, a Tesla, which is doing really well in selling cars in US, making a lot of money, they also introduced a Tesla robot. And just 2 weeks ago, there was a big conference, CES, showing up. Recently, we're working on Legged robot. This is the top dog from Boston Dynamics, working on these dog. Those are big robots. You also see small robots, swarm robot the size of a bee, a flying bee, putting all the intelligence in a flying bee, very small. And then you see robots like on the right, like Da Vinci, which has been very successful in the hospital, is along with a human, and snake robots, which can rub around and use for rescue. So there are all kinds of robots coming along. Now, last 10 years, as AI really picked up, machine learning, computer vision started working, this has seen a huge explosion. So autonomous, I would say the biggest investment is in autonomous vehicle. And I think the biggest event from US and China. As I said, in US, you've got Google, Tesla. In China, you have Baidu, many other companies are there. Now, of course, these companies promise a bit too much. And, for last 10 years, there's more than $16 billion investment. And I know Baidu has deployed robot taxis, at least now you can see the deployment is more in China. One of my former collaborators, Rui Gang Yang, he's now CTO of a company called Inceptio. They're building trucks, level 3. So autonomous driving in certain form, not full autonomy, in semi-autonomy, partial autonomy is coming up. You can see that. Other big success has been logistics warehouse, especially in US, we see order from Amazon. I'm sure in China, you're JD.com. And when the COVID came, nobody wants to go to malls. We order everything online. So the sales have gone up, but they use a lot of robots for delivery inside the warehouses. And I'll talk about that, warehouses to your home. Then, of course, there are Foxconn. And you're seeing more and more social robots coming. Recently, a couple of months ago, we have a partnership with Amazon. And I'll show you the Amazon robot is going to come out very soon. So where do we see success? So the big successes last 10 years in robotics has been actually in kind of warehouses. So this is the Amazon warehouse video.
Since rolling out the Kiva robot across its fulfillment centers, by 2018, they had 100,000 of them. By now, that figure has comfortably surpassed 200,000. Amazon Robotics has been refining the design still further.
So I don't know, could you see my video and hear the sound?
Yes, no problem.
Okay. So here's the thing you see a lot of videos like this in YouTube and show JD.com. So these are robots, they basically take shelves of material, move it around, and these warehouses are like miles long. So they got lots of warehouses, they're moving stuff around. But if you look at this video, so it's a great success story because these warehouse robots are working 24/7. Moment you order, the order will get processed, and how the robot goes and bring the shelves to the human where all the products come and they pack it together. But there's something I want you to notice in warehouses. This has been a huge deployment and a lot of commercial factories. But this has come to my title. My title is about controlling uncontrolled environment. The warehouses are friendly environments. They are made robot friendly. So the kind of robots that we see successes today are which are robot friendly. So that's a big part of my title called control. One thing you notice in warehouses, they're only boxes and robots moving. There are no humans moving. There are no other obstacles. And secondly, if you look at robot, there are sensors on the ground and they'll walk along rectilinear grids. So the reason they made them robot friendly so that robots can move it around. Now watch that again.
New iteration of Kiva, known as Pegasus, is 10 centimeters shorter, meaning more can be stocked on top and uses half the parts, so it's cheaper to manufacture and maintain. Amazon says Pegasus can lift a hefty 600 kilograms and can be customized with a conveyor belt to work in the sortation centers.
So warehouse has been a big success story, but to make this a success, they have to design warehouses which are very robot friendly. And again, you saw robots moving rectilinear grids and there were no humans. The other company, this is a company, one of my good friend, Matt Mason is involved. They had an IPO in last fall in New York, $300 million, $400 million. They're doing certain kind of factory automation. And again, they're customized to be robot friendly.
Advantage. Since rolling out the Kiva robot.
So this one I'll show you. So a lot of packaging and having some simple manipulators. So again, this is clearly, especially makes a huge benefit in factories for packaging and moving items around. So when you order something, by the time somebody came and delivered to your home in a box, robots happen. Again, so these are kind of examples, especially at least in US right now, there's a very serious labor shortage. I don't know how the condition in China, because a lot of people retire. There's a massive resignation because of COVID, and because of COVID, people don't want to work. So right now there's a serious shortage of workers, and that's lead to more autonomy. We got to do it. So this is where we have seen success of robots, but I also want you to point out why these have been successful, why many cases not successful. So as I said, these warehouses and these packaging environments were made to be robot friendly. They even choose lighting where computer vision works. There are no humans, and they made sure that the techniques have made work around. One big challenge for robot has been that there are no humans, because humans are the most unpredictable thing a robot has to deal with. If you ever want to make robots successful, keep it away from humans, because once humans come close to robot, life is challenging. And they put a lot of sensors, like a lot of sensors on the ground and lightning to make it happen. To give you an example, what is more challenging, so one of our recent project with Amazon is doing lots of things. Amazon is one of the biggest company. Not only the logistics, there's the Lab 126, they're going to introduce a robot called Astro. They just announced it last November. We are getting our first version in January. It is still not available. This is very challenging because they want to put this in your home. Now, as opposed to a factory, a home is very challenging because everybody's home has a different layout, different mess. Like this stuff on the floor, there are wires. Nowadays, people have all kind of cables, carpet. So compared to factories, robots are very hard home. So this is their video. I can show you what they can claiming, but it's not widely available yet. So this is what they're trying to do for $1,200.
A robot?
Yes.
What are we going to do with a robot?
Well, Astro, follow me.
Hi, Grandma. I miss you.
I miss you too. Hey, you got the toy I sent.
Yeah, I love it. Astro, follow me.
Cool. All right, race ya.
Come on.
So if you see this video, Amazon is a confirmation. This is a nice clean house. Now my house is not so clean. My house has too many wires and too much mess. So we still don't know. This looks nice. It can stay in a home. It can follow people around. You can take the camera. You can remotely monitor your home. But what if you have a pet? What if you have a small baby? What you have, cables? We don't know how good these robots can deal with the mess of their home. Of course, these are good cases to show. There's a camera that comes out and you can see remotely.
Yeah, turned it off.
And now I totally believe you. Ooh, yikes.
So think of the robot with a camera. You're sitting in your office with your iPhone app. You're doing it. So this is where things are happening, you know. And of course, for older people, especially during COVID, you know, people could not go home. It was very hard for older people. Your robot can be a social companion, like check on you.
Steve, remember to eat something green today, Dad.
Check.
So this is clearly a trend right now. In America, we saw a lot of vacuum cleaner robots. I use them. But again, you have to make it robot friendly. And this is where they're coming out with home robots, which can have cameras, which can follow you. And it has a small container, you know, you can even go and like give a cup of coffee or a Coke. So this is where it's happening. So Amazon took a big step, and even I think Xiaomi and some other companies have it, but we don't know how successful they would be because homes are very difficult situation. Anyway, so that's not it, but where comes the challenge? So in US, Amazon spends more than, before the COVID was $30 billion. After COVID, I don't know, on delivery. We got so many packages on Amazon left and right, and Amazon working on a delivery robot like this. Of course, this is a nice case, like nice friendly robot. So this is like, you know, they're showing nicely, it comes to your home and somebody takes it out. But see, outside the street, first of all, there are no people. If a small baby come in for the robot, if a pet comes the robot will confuse. So Amazon working on a Scout for 6 years, they are nowhere close to deployment because inside the warehouse, they could control the setting, but what happened outside your street, especially in US recently, we had snow. So if you go outside my house and I'm giving a talk, there's snow, robot can't go. So this is where challenges come up. Now, just to show this, one of the projects I've been working on, you know, with Baidu Research and one of my former students with a faculty, Japan, Hong Kong, one of the things we have been doing for many years is making robot go in complex streets. So we have been testing this all over the place. I show results. So this was in Hong Kong and Beijing. This is basically robot following a person and, you know, dealing with, on the top left is a Baidu crowd. This is before COVID, like an office setting. And the bottom was a demo we did at the Baidu Create event in Beijing on the bottom right. On the top right is an outside street. So this is technology we are developing now where robot can deal with uncertain situation where people are coming, crowds are coming. And now at least we are developing a technology where we can deal with this on control. So on the left for the easy case, but on the right is dealing with what I call different uncontrolled environments. So this is where the difference lies. Of course, what we are doing is the lab testing. And the question for us now is, can we make this robust so that companies like Amazon and people can deliver? And that's where a lot of money is going right now. So, and that brings other kind of robot. So the biggest, as I said, the money is going on autonomous driving. This is around for 12 years in US and same in China. And recently in US, you know, there's a very big shortage of truck drivers. People don't want to drive trucks, food truck. So there's the 80,000 demand is there's so much venture money going into it. But what happens is, this is a video a couple of years ago from Waymo in California. They show these videos, you know, where you're driving like this in a nice street. It's an empty street, not much traffic, well laid out roads. It does a good job. In fact, I just bought a Tesla a few months ago, and I'm testing it, you know, myself, how good autonomous driving is. So on nice empty roads, you can do it. Okay, this is easier. On the right-hand side is a video working with one of my collaborators. She's now a faculty at Shanghai Tech. She was at Yushin Ma. She used to work with Wenping Wang. And she got this video in Shandong. Now, compared to the empty roads here to the traffic here. So now you have people going around, you know, you see the traffic. On the left, autonomous car could work. That was more control. But on the right, and look at this traffic, people are following. No autonomous car can deal with this situation still. So this is again, you know, the easy case on the left, the hard case on the right. The question is, when can the robot technology deal with this situation? And that's a very big if question. It could be 2 years, it could be 20 years. I cannot give the answer. So one of the basic thing in robots, in any system, when we teach the pre-modules, you got a lot of sensors, you got cameras, LiDAR, and the last 10 years, computer vision has come a long way. Even the iPhone cameras or your Samsung phone cameras are very powerful. They're doing a lot of things. So perception has really made a big advancement thanks to deep learning. You take the sensing and you do the planning. So a lot of my work has been on planning. How do you operate? Like, how do you move right, move left, slow down, speed up? And once you make up a plan, you basically give the commands to actuators. Like, this is the actuators that move left, move right, speed up, control. So one thing that we have seen in the last 10 years is all three phases, the perception, the planning, control, machine learning has made a big impact. And of course, in computer vision, I'm sure Baucha and your group does all work in that area too. In machine learning has been a big success in vision, so that's long. But on the planning and on the control, because planning high dimensional thing, the success in planning is not as much as machine learning. People have work, I'll show you my work on deep reinforcement learning, but the impact of machine learning on planning is not as much as perception, and we're trying to understand and control. And the kind of work we're doing is, the previous work we did, like the whole mathematical models, we're trying to combine them with learning, still trying to understand what goes wrong and this is still a very active area of research. So in order to deal with the challenge of robotics is, where environment is not friendly, it's not robot friendly. Our homes, our streets, a lot of places in the world are not friendly. Very few places are friendly. So I'm going to talk about three sets of work we have been doing with different collaboration. One is excavation. Second is robot navigation. And the third, I'll talk about autonomous driving. In fact, I initially got some data from Baidu, from Beijing, but now I got a lot of data from India. India is some of the world's most difficult driving condition. If you can drive in India, you can drive anywhere on the planet. So we'll do that. But let's see, each of them was unfriendly. And the thing is, for each of them, we have the same pipeline of perception, planning, control, but the techniques used for each application were quite different. There's not one set of techniques. So each application needs considerable investment, and that's still a challenging for robotics, So how do you combine perception, planning, and control? It's not just you develop methods, how you integrate. Integration is a project we normally underestimate. We don't appreciate the complexity. Most papers in computer vision are on perception. Most people in robotics are on planning. Most papers in control are on control or control conferences. But now you're going to combine the three, and it's like Amdahl's law, any problems you face, get it magnified. That's where the challenge comes up. So this work, I told you, the autonomous excavator. In fact, the idea of this happened in 2018. I was in Beijing. There was a Baidu Create. I was working with Rui Gang, and we were showing some robots. It's one of those nice exhibition building in some part of Beijing, I don't remember. Somebody came and talked to us, hey, we deploy excavators for digging. Could you develop something? So this idea of this project came in exhibition in Beijing. So I want to thank that person, of course, I did not keep up. He came with the problem, and I did not even know how excavators work. But this was about 3.5 years ago, and let's see where we have come up right now. So just to give you a feeling, excavators, you see this, they're deployed at construction site. And mining, there's a lot of mining in interior of China, near Mongolia or Australia, a lot of mining get deployed. But just to get you a feeling, about 3 years ago, the global market excavator was about $44 billion. Mining, construction, exploration, agriculture, archaeological sites. And even in 2018, China, which has led the construction boom, there were 1.6 million excavators in China 3 years ago. And there are many more. I don't know the latest number, but it's a huge, huge market. Now, what are the challenges? Normally there's a human driver. You're working in very difficult condition. It's not labor friendly. You go with dusty condition, mining. So, and they're rock sliding, they're ground collapses. You could be working in very hot or very cold condition. There's bad weather. So this is a very difficult place for humans to operate. It's like hazardous and not human friendly. So the thing that we started, there's a paper that's appeared in Science Robotics this last summer and last August, got a lot of media attention right now. But this is the excavator from a big company called XCMG. And actually we put all kinds of sensors, So right here, there's a camera, there's a LiDAR, the RT sensor, the inclination sensor, the pressure sensors. So we took the excavator and fitted with all kinds of sensors to give us perception and force feedback, pressure sensing and computer vision. So this was a lot of, and we had to make sure they're robust because, these excavators are digging. So you got to be very sturdy, you can't take camera has to be, you can't have it loose. It was a lot of challenges to get the engineering right here. So the thing was, this system we built, we initially said, let's focus on material excavation and loading because these are still quite thing. So after about 2.5 years of work and Baidu deployed a lot of resources, a lot of engineering, we reached a stage. Now we have excavation system, which is comparable to as good a human is. It's getting, humans get tired, this doesn't get tired thing. And about last year, we reached a landmark where it could work 24 hours non-stop, day, night. In fact, this customer is deployed it now. And I just learned from Liangjun today, they use it for 6,000 hours. So this is real robotics on the side. Autonomous cars go for a few little. This is reaching a level, and I'll tell you why this we can do and what we cannot do. So this is a big mark in robot construction that we are reaching a stage. How do we do it? So again, what do we do? As I mentioned to you, so clearly we put a lot of sensors, perception sensor, planning sensors. We have a big perception pipeline, high-level task planning, motion planning, and control. So this is the same pipeline. But even the perception, we have a LiDAR, we got multiple camera, there's 3D parsing, 2D parsing, localization, inclination, pressure data. It's a very complex perception system. Then high-level job. So do you want an excavator for waste disposal, for loading, for rock removal, or trench digging? So these are like 4 big tasks. There are more tasks we can do. Then for each task, we come with a series of what we call low-level planning, motion plans. And eventually you go to the analyzer. So this you can see is a pretty complex system. Lots of ideas, lots of effort went together to put it together like this. So one of the things here was actually dealing with even things like perception. So when you're digging, a lot of dust flies. It's like your face gets fuzzy. So we had to develop better perception system which can operate in the presence of dust. So we actually came with a method like this, a machine learning, deep learning system. This image you see is noisy and dusty, but just like, in computer graphics or in the deep blurring, there are a lot of papers in vision graphics. We see something called de-dusting, and remove the dust. How you classify the material? It could be mud, sand, hard rock, or soft rock. There are all kinds of materials. How do you make perception stronger? Semantic segmentation. This is grass. This is mud. You want to do here, and this is water. You want to avoid the water. So when you're digging, water can come up. So you have to every time do semantic segmentation come up, and not only pre-dissemination, then you need dissemination. And finally, based on the material you have, if it's hard material or soft material, you come up with a pose, like when as a human do it, but now you do come up with the right pose depending on the material classification. So there were a lot of challenges that we came up. So we had to do a lot of computer vision for this application because there are not many people who worry about dusting or dusty material classification. So this is just one of our deep learning based de-hazing pipeline. You see that right here, and you have atmospheric, a clean image, transmission, typical deep learning method that you see right here. Input image like this, and you get a clean image. What I call clean means you remove the dust, and a lot of training went in there. This is it's all in the paper, you can see the details of that. So this is example of on the left, there are videos here. Again, I don't know if you can see, let me go back again. So this is the original image, you see a dusty. And when we do de-dusting or enhance the image, this is what it looks like. It's something like, think of deep blurring, a lot of work done in graphics and vision. And this is on the top, dusty and the clean, because we need to do material recognition. If everything is dusty, we cannot recognize it, right? At least not for computers there. So this is again, different terrain data sets, dry soil, wet soil, mudstone, titanium. You see 8 different cases. There are many more. So we had to actually then go and build our own databases because in typical computer vision research, people work on object detection, people work on face detection, people work on action recognition. Those are big problem in vision. Not many people in vision cared about different materials, especially in the mining side. And this was more difficult application, so we had to work around it. And there you can see more and more details about how to do it. Pose estimation. So especially if you're given a big rock, how do you know how to dig around it? If it's a big rock, you hit the rock, your excavator will get damaged. You have to go around it. So based on material classification, we had to do a lot of special methods to what we call 6-stone pose estimation from there. So this is like a real-time terrain reconstruction. This is the terrain. Before excavation, you start digging. This is after excavation. And you compute height maps, and you can see lots of, as you pile the stuff and maintain, the terrain elevation changes. So lots of outdoor computer vision and planning has to go together. And then more recently, we worked on what we call terrain traversal. Like if you look at the terrain, mostly how does the excavator move around and dig? So you have to plan the motion of the excavator, how it moves, the wheels, and then how you do the digging, this job. So this digging, how you hit and where you hit and how you move, all this was mapped to what we call the terrainability, how traversal the terrain is, how you do it. Humans can do it, but this was challenging for the excavator. And again, you'll see a lot of data sets. We have collected our own data sets and build labels them to literally do it. So we also released some data sets called, one of them called autonomous excavator terrain data set. For other application, it's pretty common in vision to this kind of stuff. There's about 30 minutes of video when a human operator is operating on the website. So this is very challenging here. This is again combination of 2D and 3D computer vision methods, semantic segmentation, well-studied problem, but how we combine the image information and the 3D geometry to figure out the traversability of a terrain. So this was some of the big challenges. We had to really solve the problem. Once you have the perception part done, the perception and traversability drives your planning and navigation, how traversable it is and how you plan the trajectory. So the output of the planning or perception feeds to planning, and the planner has to adjust based on the perception. The integration between perception and planning is a very key part in these kinds of problems right here. So again, this is the planning part. As I said, high level and low level planning. Task level planning is high level. And you break up into, to combine this happen, we use a lot of robotic literature. So each of this module, which I'm now going to show, is called a material removal task planner, base movement subtask planner, planning the arm, planning the base, control. Because excavators have a lot of degrees of freedom, and we do different kind of high level, low level planning for different parts of the excavators and see how it goes together. So this is again taskness, because a lot of one thing is you learn from how humans do it. So we look at how humans look at terrains and dig it up. So literally, we also look at task demonstration, take a lot of human knowledge there, use that knowledge to drive how you do it. So again, a lot of expert excavation come up, and we use that knowledge to really drive the system. But one part is motion planning. So this is some of the work I've done with my student, optimization-based planning, which can deal with a lot of dynamic obstacles, which can come up. And the basic technique that we use here is what is called stochastic optimization. So I'm giving you a very high-level idea. I don't want to go into details of that, but a lot of these planning modules and a lot of perception modules and are really using previous ideas and applying this to domain. And more recently, finally, we had to do inverse reinforcement learning for learning the function way. So there were a lot of different modules that came together. So this is, for example, to show you on the left is a human applying this, how they open up the mouth here and do the digging. So on the left is the human version with the expert human. On the right is our own automatic. So see how as it moves forward, how it changes the angle. So on the right was to show that how can we do the control. So it slowly changes the depth and it comes close to human performance. So this is where a lot of effort went in to optimize the perception, planning, control, so we can reach the human level performance in this situation. So we also test, as I said, one condition is when you dig, water comes up, or even there's wet soil, they can damage it. So we literally had to make sure, we also, especially if you're working 24/7, and I said, these are not friendly conditions. So you have to make sure your system can work in different weather conditions and terrain operations right here. So this is just to show you how we did it. So we wanted to know how close when we come to a human. So there are three kind of excavators we do. The smallest one is called 7.5 ton. and the very large one is about 49, 50 tons. So we literally did a comparison that if a human operates for 2 hours, how much excavation sand it can do, how much loading you can do. And literally we saw that for the small case, our efficiency is very close to an expert human. Now in the middle and high case, we go to 86 or 90% because these are bigger excavators. So the control and how you optimize the motion, we are still like say about 10 or 15% away from efficiency, but still, this is running 24/7, whereas humans get tired and can make mistakes. So this example, we showed this in Las Vegas 2 years ago. CES, you can see that it's coming and digging, except there's no human. So this was the first large-scale demonstration. You can see they move the equipment. It basically goes, figure out how to dig. Now this is not real time. We're playing 3x, so it doesn't work that fast. So perception does take time. So this is 3x video speed, but see how it's basically automatically computer-based, no human digging and loading the truck. In fact, now what they're doing is this truck was human-driven, but now they're also deploying autonomous trucks. So they want to automate the entire mining, digging, loading, and transfer of the material. That's what's coming up there. This is the condition in the indoor scene. You can see there's a lot of sticky and toxic material, which is unsafe for humans. So on the left, you see the thing. On the right side, if there was a driver sitting, except there's no driver. So again, the 3x video, but again, you can see how we're operating it. There's virtually how it works. So you can see literally how it digs up and does things. So this is a waste disposal application. We were doing it here. And this was showing, we basically ran for 24 hours video recording. You'll see 4 times. On the top left is midnight, 12 o'clock. Top right is 6 o'clock in the morning. Bottom left is noon, and bottom left is evening. So we really want to show the videos. You can sunlight condition changes, and you will see the sand moves because you're moving and digging from here to here. So this was to really demonstrate, indeed, in these settings, it can work well. So this, there are a lot of lessons to be learned from here, so this was an application. I will say one of the reasons we have had success, and I'll tell you why, what works, what doesn't work. These excavators operate in isolation. So remember I told you a few minutes ago, there were no human or human operators nearby. So the fact there were no humans, literally I say, thank God, I won't hit anybody because I don't trust autonomous systems. So I didn't have to worry about hitting, which I'm going to face on driving. Is it a question?
No, not really. Probably someone didn't turn off the mic.
Okay, all right. But any question, ask me. So the good reason why we're able to make it work. So customer, we're dealing outdoor scene, a lot of terrain materials. So we could take the thing, get all the label data, make the pipeline, and they were an excavator. They were like 4 or 6 level, high level task planning, digging, moving thing. We could come up with the algorithm for that. So we could automate the perception pipeline for outdoor terrain because it's still outdoor terrain and water. We could do the perception pipeline and control. So because those modules understood, we could develop those solutions for specific application. We can combine learning and planning and vision, do it, and there were no humans. So part of the reason we succeeded is because these are there. And last but not the least, excavation is more like you're digging and pouring around. This is not fine manipulation. So if I give you a robot task, let's say when you put your shirt on, you button. When you put the button like this, that's a very fine manipulation. That's where robots struggle. They cannot do the fine manipulation. Or when you put your shoelace and you tie your shoelaces, the robot hardware cannot do fine manipulation. Fortunately, in this case, we just have to do the digging. It's like a big excavation. And it's not a very fine precision task. We just do most of it like humans do. So this is lessons to be learned. This was a success, but why it was success? Now, if you give me a very difficult construction job, people come to us. Can you do a construction job? And many times I say, we are not there yet. So there's some successes we can do, but construction has so many complex tasks we cannot do. So this is, lessons to be learned. what is doable and what is not doable. And one has to be honest about what is doable. So that was first environment. The second thing, we did a lot of work on navigation and indoor and outdoor scenes. So this is where I have a lot of projects going on. This is work I started with Japan and Hong Kong, where lots are going around here. So as I said, we see a lot of the robots operating. Even now, you'll see some demos, a robot delivering food in a college campus, a robot in the airport. But whenever you see these videos, commercial, these robots are working in empty space. Like remember I showed you Amazon Scout. The challenge is, can this robot operate in a dense crowd? Of course, there have not been many crowds because of COVID, but this is our building. So we took a robot and we say, can we make this robot dense crowd? So what we did was, this is a turtle bot. There's a LiDAR here, there's a depth camera, and you see a laptop here with some very clumsy tape around it. Why? Because we're using the sensors from these cameras and these LiDARs, and this laptop is my wonderful GPU. I'm running my deep reinforcement learning. So we built the system, there were sensors, but there was this GPU in the laptop, and imagine I pulled laptop on top of this thing. But now industry is coming with very strong AI chips. So will this come up? But this is what we do. So our goal was, can we develop perception and planning technology so that this robot can move through a crowd just like humans do? That's what the real goal was. So as I said, we developed a whole system called trajectory prediction for, advanced DRL. DRL is reinforcement learning, collision learning policy. It takes into input the LiDAR. It's an indoor LiDAR. Of course, they're getting cheaper. A depth camera we use, RGBD. We have some goal location, where to go. And this is it, and you compute a robot motion. So what you train is basically a deep reinforcement learning called collision avoidance policy. So the goal here was, how can we design a smart policy which can deal with a sense of crowd? Because when you're in a crowd, it is very hard to predict how a bunch of humans work. And humans can sometimes be mean. I'll show this to you, comes up here. So we started with a lot of components. There's been a lot of work on pedestrian tracking. There's a very popular Euro tracker, mobile, we use that. So we look at all the pedestrians and we predict that this person in 2 seconds is going to be here based on speed. This person will be here. We predict where this person is going, and this, even humans walk, in our mind, we silently predict where the position is going to be. So you do the tracking, but you do prediction, where they're going to be. And this is used for the reinforcement learning policy. So how does this work? Let me show you the video here. This is a system we published a couple of years ago. And I'll explain to you what's going on here. It's a lot of effort going in here. And I'll show you the simulation used to do it. So this is our robot. This is a computer science building. It's a new building at Maryland a couple of years ago. And you can see it's moving. And some people are mean. Say they put their foot at the last minute and the robot needs to avoid. So this is totally uncontrolled. You know how students are on a campus. This is before COVID. And the robot is navigating among the people. This is real-time video from 2 years ago. So the good thing here was the robot was flat, the ground was flat, but dealing with lots of human components. So the tracking and prediction. But you have to take all these components and make them work together. So this is showing the pedestrian tracking. Tracking is pretty mature. There are a lot of trackers available. We use YOLO 3, and I'm sure there are more trackers coming around like that. And this is a mapless world. You go to a place, robot doesn't have a global map. Unlike Google Vehicles, how we do things there. And then we go this, I'll speed up the video in terms of time. You can see how the tracking works. And the second thing was, so how do you train it? So I had done a lot of work on simulating crowds, human behavior. So we actually built a simulator. So this is where, me and Biocham talk about metaverse, so VR. This is a simulation environment. This whole policy was trained using simulation, what's called sim to real. We look at sensor simulation, we look at different kind of movements and train the robot with different kinds of human motion. So we train in our simulator and based on the policy go to real. So the more accurate your simulator is, the more better your runtime behavior would be. And we also simulate, like the depth camera has a field of view. Sometimes the human come in front of you, how you go around the humans. So this is how we train the robot to different, and especially, it doesn't get to oscillate. Like sometimes humans can be mean. So robot has to go around it. So this is where all the simulation that we do in graphics and VR became very useful for training these kind of similar. In fact, a lot of people nowadays use game engines like Unity and Unreal to do these kinds of great simulations. So this is where more simulation, and I guess whatever more metaverse comes up, that will affect the robots there. So this is, dealing with what's the problem called freezing robot, that if a human comes in front of a robot, will freeze. And literally, like it's imagine you're being so mean, you suddenly go and stand in front of the robot. This was being really the nasty case, all of a sudden come, but if you can anticipate, it can go around it. So this is walking in real time. And unless you're really mean, you do it. But we also test in difficult situations like corridor. Suppose the T-junction, you see a situation like this, robot is going, and it's a very narrow corridor. You cannot see in the front as it'll go. And if somebody comes around, it goes around it. So the reason we could do all this situation because we were able to simulation. So as the simulation capability improve, this will get better. Now, more recently, we have been doing a lot of other tests like bartender. So we have been deploying this robot social event. So there was a big opening of an event. Our governor came, and this is a robot.
Oh, good, no worries.
In a real crowd, and it's going around taking like COVID sensors and chocolates. So you have a robot going to the people, and people of course play with it. You can see my student do something with it, and literally serving you items like giving you water or giving you food, or if COVID, giving you hand washer. Or something like this, this is the cover in the media here. The robot comes to you with water. And no, if you don't have a mask, so like Bauchen, you were telling me some people in the cafeteria don't wear masks. This robot can take the mask to them. So you can do computer vision, people don't have a mask. Robot comes to you and offer you a mask. So this is, please have some water or please use a mask. So this is now we have technology where robots can work indoor crowds and do delivery items. So we're at least getting close to that. So this is where a combination of simulation, computer vision, perception, planning come together. The good thing again is, this robot is small, it moves slowly. So it's not like excavator, it's not like a vehicle, so it will not do damage. So again, I'm happy because my damage is limited. This is where
no worries.
And this is more recently we developed, like when COVID came, so we developed a robot, robot walking around. I did some work indoor at UMD, and I did some work with my student Japin and outdoor. So Japin team had a dog robot that also got covered. This was in the media. In fact, CNN wanted to come and footage it because COVID is high. So basically the idea of the robot, it walks around and see when people are not maintaining social distance. Of course now masks have come up, but initially when US keep social distance, 2 meters. So it look at people around you, and if you don't maintain social distance, and it'll tell people come and wear. So detect people not maintaining social distance and warning them, it's like you're not being good or you're not in mask. So we have the robot technology now. This is working in our offices. You can see the furniture, there are people, it can deliver stuff to you, social distance. So this is where we are making advancement. You have good indoor navigation capabilities. You can do for delivery, you can use for social distances. So the different applications, this is like in our lab, we were doing experiments, but we could not take real people because of COVID protocol. We just put this cardboard human, but we can do a pretty good job of detecting where people are doing social distance. One thing that came up, I'm very interested because the pandemic is coming. You could deploy these robots in public places. Of course, privacy issue comes up. Could you see signs, can you see people are sick or you see some viruses? So the robots can also be used for mobile sensing devices in the future, how things do like this. So this is where when the robots can move in crowds, they can do sensing, they can delivery, there are a lot of possibilities right there. So that's something we're doing. But again, the challenge is outdoor scene. The indoor, the good thing was your floors are flat. We're dealing with people. When outdoor, this is on our campus. There are not many people, but the terrain is very difficult. The terrain is uneven, it's muddy, it rains. So this is now a robot, it's not very powerful. How can you go up the hill? If you take a wrong path, it'll get stuck. So how do you look at the elevation of a hill? This is now on Maryland campus. And again, we use simulation. This is Unity simulator. We use a simulator to do the dynamics of the robot and figure out what paths to take and what paths not to take. So this is the kind of examples, we're doing. We're using simulation to train the robot for different situations. So dealing with outdoor terrains, so this is like saying how robot is moving. So when you move, Like there's a tree, how a robot cannot go on deep roots. So if you go on the right, it'll get stuck. But on the left, with our smarter policy, it goes around the roots. So how to take a path the robot can navigate? You see this slope, because the robot is not powerful, it can get stuck. So these are wheel robots, and now we're getting the dog robots because Lego robots can do more things than wheel robots comes up. So this is where we want to develop technology. Robot can work in complex outdoor crowds and uneven terrain. I think uneven terrain is even harder problem than crowds, because the unevenness of terrain, sometimes robot cannot go up, and it could be slippery, it could be a rainy day. So there are a lot of challenges still that we're working here. But last but not last, the thing I was talking about autonomous driving. So we see a lot of autonomous driving. As I said, a few months ago, Baidu deployed robot taxis, but they're in some parts of Beijing which are very nicely mapped, which are friendly. I'm sure there are parts of Beijing which are challenging. But for our work, I got data from India. India is very interesting. You see this road condition. First of all, you don't see any lane signs. Secondly, if you look at the vehicle, there are cars, there are rickshaw, there are pedestrians, there are buses, there are even animals. So it's like a totally mixed. You can't predict the animal would work. And thirdly, people don't follow rules. So how do you deal with the situation where it comes up? So first thing we did was tracking. How do we track all kinds of mix of population? You see the cow, you see the vehicle, you see the bicycle. The only thing is when you see a person sitting on the bicycle, my computer vision can track the motion, but it doesn't know that the person on the vehicle moving on it. It doesn't have semantic information. This is a bicycle and bicycle rider. It treats them as two different objects. So the first tracker we built, which could really track very dense, heterogeneous environment. Most of the autonomous cars, you see only cars driving in lanes. This is what I call chaotic traffic. So this is one of the things we built. And again, we build a lot of ideas from planning, how dynamics of the vehicles move, and build that deep learning network. So again, taking knowledge of dynamics and planning and motion prediction and combining them in this kind of a framework like this planning. This is like example I showed you. This works well. Now we can track, except, the only thing is it tracks this bus as one moving entity, and they think of the person as separate. It doesn't know the driver move with the bus. So it tracks them as two separate. It's just like this tempo. This tempo is one object tracking, but the person standing, it thinks is a separate moving person. So this is the kind of, computer vision is getting better, but computer vision is not smart as human to make this relationship automatically yet. So other thing is a big problem is prediction. It's a pretty well-studied problem. So this is a paper we published in a few papers in CVPR a few years ago. What we were targeting was dealing with very dense traffic. So these are dense data sets you're seeing from India. In fact, just last fall, we released 100 gigabytes data of India with roads like this, with no labels, with all kinds of traffic, buses, trucks, tractors. And how do you predict the vehicle? So when the density goes high and you got big vehicles like cars, bicycles, scooters with different dimension, that makes your problem of tracking prediction harder. So our prediction was traffic, and we showed this red traffic is pretty close to ground truth. It's not perfect, but it's much better than state of the art to do a much better job here. And other challenge which is coming up in traffic now is behavior. So you want to know the person driving next to you, is that person aggressive or not aggressive? So can we label the behavior?
We are presenting an approach called Graph RQI for classifying driver behaviors using graph spectrums. Our input consists of the trajectories of road agents, and we classify the behavior of the driver into one of 6 different classes. Our approach consists of representing traffic as a graph and computing the spectrum of the graph using a novel eigenvalue algorithm in linear time.
So this is using spectral analysis. We map the behavior from psychology literature to this thing. I'll show you the video quickly on the right side.
Traffic rules. This also serves as the main motivation behind this work.
So you again look at dense traffic on the right.
On spectral graph theory. At any particular time step, we represent the current state of the traffic through a graph. In this video, we show the graph for one particular road agent. At the next time step, we update the graph to account for new neighbors. We then compute the spectrum of the Laplacian of this graph and use the spectrum to train a multi-layer perceptron using supervised machine learning. The results of our method are demonstrated next.
So you look at relationship between them, you build a proximity graph, and based on the spectrum analysis behavior. So this is taking a lot of linear algebra to behavior. So we have published quite a few papers on how to behavior modeling and coming up with a mathematical framework. Again, I'm just giving a high level view. I will skip the details of that. So this is, come up. And last but not the least is, when you drive, we're dealing with very difficult, unsafe situation. This is like when you fog, rain or snow, like it's winter time in US, I'm sure same in Beijing. How do you find safety to navigate? So this is again, something we have done for safety because urban safety is a very big problem in many places. Accidents occur. So how can we detect unsafe condition? And it's just like this. So I think, it's a very overview talk. But again, the problem I want to hit here is that in autonomous driving, urban driving is still a very open situation. Because you have a mix, the two big challenges that come up is if it's only cars, life is easy. But even when I go to Beijing, there are a lot of bicycles or there are a lot of pedestrians. So when they're bicycle or pedestrians, they're slow moving, they're more vulnerable. How do you deal with that? That's one thing. In fact, one of the projects I'm talking to, there's a new AI institute at Peking University, and what they're building is very impressive stuff. On one hand, your cars are getting all the sensing, to make it, but they actually make the infrastructure friendly. So there are a lot of projects, especially I've seen in China. Well, what can we do in the infrastructure to enable autonomous driving? Because I think just relying on the vehicle alone is too challenging. But if you've got smart lights, smart sensors, or something that can guide the communication. So the way I see the future in the smart cities is that all the sensing will not just be in the vehicle, but also in the infrastructure. So there's a nice project I'm working with folks in Tsinghua University. We're starting on what infrastructure you can build. If you're to build a city for the future, which is autonomous driving friendly, remember, robotics only works if the environment is friendly. The general purpose problem is still too hard. And that's why all these level 4, level 5 claims are really crazy. So the question we are asking is, we have worked in autonomous driving for 10 years. It's still very limited because there are a lot of humans, a lot of crowding, lots of rules. What can we do to make our city robot friendly, autonomous driving friendly? So this is a really great question where people are asking, because you need that friendliness that's to success. Because AI is good, but it's not really AI. Machine learning and machine learning is good as data. It's not really a smart system. That's what you come here. So this is where, I want to conclude. I love to take questions. So as I said, robotics is an old field, but all the advancements in the last 10 years, the sensing technology, the computer vision, the machine learning, clearly have huge impact. Like this autonomous excavator, 12 years ago, we could not do it. We did not have all this computer vision, machine learning, planning there. Now, all the robotic system, I give you example, excavation, indoor navigation, autonomous driving, they all involve planning, perception, and control, but solutions are very different. Now, even though my excavator works in some situation, but you could bring a whole new kind of material and my computer vision could fail. So anytime you discover a new kind of material, I got to train it again. I can make it work, but there's a challenge is there. But remember again, all these AI autonomous systems, while they sound very good, their intelligence is poorer than of an 8-month-old baby. They don't have common sense. And this is where the hype of AI is bad. It's not really AI, it's machine learning, data-driven system. Your performance is as good as the data you train on simulation or whether real. So uncontrolled means, what if you come with a totally new situation? And this is where none of the systems can give guarantees. So and one of the things people don't realize when robotics, so part of robotics is algorithm, but a lot of robotics is a system. How do you build robust system? We do not have good mathematical foundation of building strong system. Most of this integration is ad hoc. So this is where, how do we combine perception, planning, and control and do things? So this is, of all the students hearing the talks, this is the area full of gazillions of PhD topics. There are more challenges than what we can do. So hopefully, I've hopefully convinced you that things have come well, but still a lot of work to be done. And I'm sure the future students will come and solve this problem. That's there. So one thing I should also mention to you, as I say, I work with Baidu Research. They have a big lab in China and here, especially for these projects like autonomous driving and exploration. They're looking at if you have full-time jobs or internship, there's a group there. You can talk to Liangjun. I don't, he's a full-time guy doing there. So I will just stop here now. Questions, comments, feedback, ideas, suggestions, I'm open to everything. Thank you very much for your time.
Thank you. Yeah, thank you, Dinesh, for the wonderful talk. So any questions from the audience, both local and online? If there's any question online, let me know. Okay, yeah. Hey, by the way, I give you statistics. Collectively, we have about, well, the peak level with the audience, close to 1,000 audience watching your talk. So Dinesh, your message is get the wide across. Okay, well, maybe I pick up on your very last note you mentioned, but not speak much about it. Is the infrastructure design. Yeah, so basically in between controlled, fully controlled, and uncontrolled, there's this infrastructure building, sort of sitting in between. Can you say a bit more about it? I mean, people are talking about it. I wonder, is there any principle going into this? I mean, you can always, add up lights, intelligent lights, the road, even the road design and all that. But, what are the priorities? What are the economical considerations going into this and everything? Maybe, well, I'd like to hear more about it. Do you have anything to tell us?
Yeah, so that's an excellent question. As I said, the key rule and find, robotics systems work well when they find the environment friendly. So that's a very broad statement, and what does friendly means? So when I showed you the videos of, for example, warehouses, right? So I showed you the videos of warehouses. Now, warehouse is a big success, but the reason warehouses work well, because if you see here, they make them friendly by no humans, but actually you may not see there are some RFID sensors on the floor, which can help the robot guide. Typically, you will not put RFID sensors in your home or your offices, They put sensors on the floor, they put cameras, and why all the robots are orange? Because the camera and computer vision work well. So they literally did a lot of things in warehouse, put sensors, lighting, colors to make it work well. That was one example. Now, if you look at autonomous driving, industry spent $16 billion, and there were all this projection, by 2018, 2019, level 4, level 5, where it doesn't happen. So if suppose, you build a lane, let's say you build a lane between Beijing and Shanghai, you lock the lane like a toll and you say autonomous cars only, no human drivers, no bicycles, no pedestrians. It's one lane, only autonomous car. I would say, Baochen, the technology can solve the problem. But when humans come around, no. So one infrastructure you could do is, okay, this autonomous cars, no humans. Now, there's a big thing in autonomous car, people doing, vehicle to vehicle or vehicle to communication thing. Like when you're entering lanes, when you merge traffic, like your traffic light, how they do it. So people are trying to deploy the sensors on the roadside, which your vehicle can communicate with. They give you information about the sensors because maybe there's a camera in the front. Who can tell you of the drivers around you? Are they aggressive? So, as I said, to make autonomous vehicle work robustly with no collision, you need a lot of information or surrounding around you. The car sensors gather it, but if there's a sensor on the road, they can gather it. So this is where, what I call infrastructure. Like even I showed you the delivery robot, right? If it's flat ground, I can do it. Indoor robots, I can do it because your floors are flat. But if you go on even on Beijing campus, you got some big sidewalk, somebody parked the crowd here. So it's dealing with difficult situations. So if you can remove those difficult situations and put more sensing, that's where robot could work. That's what I'm saying. But it's still very application specific. There's no generic universal answer to this question.
All right. Yeah. Thank you.
Okay. Hi, Dinesh.
Go ahead.
Hear me? Yeah. So I would like to ask a question. Thanks again for your very inspiring and impressive talk. From your talk, we have seen a lot of successful, deploy of robotics in outdoor scenes, like, for example, your like autonomous excavator, and also the robot taxi, etc. And I'm wondering if we can pushing the robot further also in indoor scenes. Like as you show, we have the Amazon Astra, right? It's like a dog. It can follow you, and there is a screen you can do video chat. But I think the ultimate dream of a robot would be home robot, like who can assist you to like do housework and like cooking, a lot of things. And I like, because here we do a lot of object perception tasks for objects, object manipulations. I think I would like to like hear some advices or lessons from you. What can make a home robot works? What would be important research topics to get it working? I know this might be too broad questions, but I do want to get your opinions on it.
Yeah, so so I tell you, if you look at all the success stories I've shown, now excavator was different. The excavator was a big, like a big, digging. It's not fine precision. But if you look at autonomous vehicles, it's basically some robot on wheels moving. If you looked at the warehouses, robot on wheels moving carts with them. And even when I show my robot navigation in the crowd, robot is moving. And even you see Astro, it's basically big wheels and small cameras. So these are all motion navigation tasks. Your robot can move around. Now, for home robot, so robots are good at moving and shipping things around. We're good at that. None of these robots have what is called good hands. So, as you mentioned, home tasks, right? So one place robots are doing well, we can move things around, we can navigate among traffic, we can navigate among elevation, But this is called grasping and manipulation. This is one area there is still no grasping solution. As I told you, you want to put your dishes, you use hands. So any job where you use your hands, we don't have good hands hardware.
I see.
So everything I showed you was moving, delivering with wheels mostly, right? And maybe now Boston Dynamics spot robots are still moving. So one of the holy grail robotics, the feeling was now people are trying deep learning recently, but the general feeling was for 30 years, the grasping field has made very little progress. So imagine, I can give you manipulators. Manipulators are $50,000. Even if you give me 2 manipulators to me for free at home, they are virtually useless for me because these are arms with no hands. So think of how much we as human, we type with our hands, we write with our hands, we eat with our hands, we cook with our hands, we put our clothes with our hands. So any job where you need good hands, sorry, we have people are working on it. And for example, Amazon can take items together, but they have to take them item and pack them in a box. Same as JD.com, how you pack up the box and put tape. They tried with picking challenge, they did not succeed. Now, if you have a solution, you know what? Amazon will give you at least a $1 billion. Easily, they paid Kiva. So if you can do the job of packaging boxes and shipping and taping, at least $1 billion, that's a market. So this is what I'm telling you what the potential is, but we don't have a good solution.
I see. It's quite challenging, it sounds like. But I think there are a lot of research works going on. And,
Absolutely.
Yeah, it's like Tesla is also building this humanoid robot. I feel, and also a lot of people are like looking into dexterous manipulation, like dexterous hands. Yeah, I think there will be a lot of interesting topics to further the research. Yeah.
No, this hand manipulation is a classic problem. Every time you go to robotics conference, you'll see 50, 100 papers, you know. I'm just saying, you know, certain problems are just harder, you know, with planning, moving. See, computer vision was very difficult 10 years ago, but deep learning made it easier. So maybe somebody will come somewhere manipulation. Maybe in 5 years from now, somebody will come with a smart idea that will become mature. I'm just saying, as of now, it's hard. People are working on it, but just like computer vision was changed by deep learning, deep reinforcement learning having some planning tasks, somebody may figure out how to do manipulation with some different kind of learning, and that can happen anytime, you know. But I'm saying this is where a lot of challenges lie today. So as of now, and that's why you see Astro, they build a robot which can move with a camera comes up, but it has no hands because there's no practical solution Amazon can deploy right now.
I see.
So a lot of problems there. Maybe you guys can solve it. I'm just saying, but on the good end, I don't want to be negative. I'm saying, here's a potential. If you could even come with a good, partially good solution, it has huge research and commercial impact. Billions of dollars. It's huge market for Amazon.
Yeah. This is good news from the industry side and can shed a light for us on what topic we should do for research.
Well, so one of the things we're looking at robot construction. So excavation is just $400 billion. You know, construction is a $10 trillion worldwide market. Even if you can do 10% of construction tasks robotized, only 10%, you're talking about $1 trillion market. So there are a lot of jobs in construction. See what jobs you can do. There are lots of jobs you cannot do. So we found excavation. We said we could do this. So identify the problem which are doable and then solve them.
Any more questions?
Hi, Professor Dinesh. I'm a little bit interested about the integrated effort of the whole system of the robot. You know, sometimes, for example, for the autonomous excavator, there is a complicated system combining of the perception, planning, and also the execution. So from your talk, I think the whole system is split into many parts, from the image processing to the simulation or something like that. But if do we need some integrated effort to make the whole system work? Do you need some, for example, end-to-end refinement, or you just add all the parts together?
So that's a very good question. I don't have any easy answer. So this was a high-level pipeline I showed. You can see my slides, right?
Yeah.
Okay. And even like, so this is a solution for the excavation. I would say this solution that we have come up with was customized for excavation tasks. So right now, you know, we had to develop these modules and integrate them for this application and test them. But this is a great question because there's a lot of research in perception, a lot of research in planning and control, but there's not much formal research in combining and making them robust. So this is the area which is, again, a lot of work needs to be done. So right now, you know, we did it for excavation. The car companies are doing it for autonomous driving, you know, they're looking at those applications, doing things right. So those exist. But in general, you know, how do you build robust? Because remember, the challenge is there's some error in perception or some error in planning or some error in control. They all get exaggerated. The 3 or 4 module is like Amber's law. One of them fails, the whole system fails. So we have to make each part robust and interface robust. So right now, your question is excellent. There is no automatic way except people do it for customized, you know, for navigation, for excavation, for autonomous driving. But there's not much story. So this is where the people are finally paying attention to it. And maybe you will see more research in the coming years.
Okay. Yeah, thanks.
You should solve it for us. Lot of problems.
Well, Dinesh, maybe a specific question actually. I noticed that you have a robot climbing up a little rope. Well, a landscape. Yeah.
Yep.
Climbing up a landscape. Yeah. Well, how do you ensure that it doesn't get stuck into like local minima?
So yeah, so this is one of our big projects. We have a huge army funding project. And army is interested in going to what we call jungles, forests, right? Terrain, right? They go tracking, right? So when Google drive their cars, they drive their cars in nice, friendly places. So this is what you're talking, it doesn't get stuck. So this is actually the robot we are working on. It's a great question that, so this is a robot, there are a bunch of tree roots. And this path, the old planner went up the roots and actually got stuck. So that can happen. So your question, excellent, Bauchen. This robot, it got stuck. The robot is not powerful to go some elevation. So what we are trying to do is be conservative. We look at the elevations and we make an estimate, what is the elevation, what's the height map, how much force and dynamics will be needed. And this robot is probably not, it's like, your car gets stuck, your bicycle gets stuck, same thing. So there is no automatic solution to that. And in fact, what they want to work on is, imagine this is a clean grass. You can see, sometimes you're walking on a tall grass. See, you will walk, suppose you have big shoes. You can walk on tall grass and you'll take a slow step and see the ground is wet. You have the touch feedback. You can't see the ground, but you can do it. How do you make robot do it? So these are all, Bauchen, really, really good questions, because, and sometimes what humans do is, if today rain and snow, you smell it. If it's a rainy and snow day, you probably walk slowly and carefully because your brain is trained. It's a rainy day, ground is going to be slippery, watch out, right? Same thing like that. Robot doesn't have the sense of smell. So if you look at how humans navigate, humans are multi-sensory, much smarter. Robot sensing is very primitive. And robot doesn't have sense of smell, doesn't have a good sense of touch, and just estimation based on perception, which is not perfect. So clearly there are cases where actually we tend to be overly conservative, and if it's too steep, we won't even go there. So this is exactly, what we are doing, but this is, you're asking, all the questions you guys are asking, I wish I had good answers. These are all open problems.
Well, another question. I have a lot of questions. If you're here, I can ask you.
Please do.
Any more questions? Well, maybe just one more. Boston Dynamics, right? Doing all the kicks and jumps, every year they roll out the video. Seems to be very impressive. So where do you see they're going? And what do you consider their central sort of technology? What lies, as the central technology for Boston Dynamics?
Yeah, so Boston Dynamics are releasing these very good videos. One is humanoid and one is Spot, the dog robots. You see them all the time. And somebody has told me, those videos are like, it's like movies, but again, I don't know. It's interesting you asked me this question because right now, so for this project, this project, like you see this robot I'm doing, it's a Husky, it's a wheel robot. Now, we just placed an order for 2 Spot robots. Just this month, there's a model called Explorer and there's a model called Enterprise. In US, they cost about $150,000, $180,000. Now, I'm getting those legged robots because the legged robot, I think definitely they have some really good control technology. The control and balancing technology is really amazing because I've seen the Spot robot and right now you can control it with a joy box. So it can go up and down the stairs. It can do amazing things. So they definitely have some really good control technology. What I want to do is make it autonomous. Like not a human should guide it. It should remotely go and do it. So ask me this question in 3 months when I'm going to get 2 Spot robots. They're not cheap. And what the experience is with that. It's definitely a very, so Legged platform is finally the new platform. All the robots you see are wheels, but these are robots with 4 legs. Each leg has 3 degrees of freedom, but they definitely have good control technology. So it's definitely much better we're going to play with that. But, till they were bought by Google got rid of them. Then SoftBank bought it, they bought by Hyundai. Their technology is still not made to mass market. So you can always put it, it's like Amazon. Even Amazon, I'm working with Amazon Astro Group, they're not selling it. They just put a video, they're going to give 200 robots, just people to test it. I don't know this Astro will work in my robot. My home is too messy. So these videos are nice, but till you really test them, no. But in the case of Boston Dynamics, ask me in 3 months because I'm in 2 spots and maybe I may have a better answer for you. But the videos they book are really nice and they don't publish paper, they don't tell the details. So it's kind of a guesswork.
All right, well, I will keep it in mind. I'll ask you in 3 months.
But I'm getting 2 spot robots. I hope they come in time. And it's funny, I'm asking them for more details. The funny thing is, they are giving you very limited software development kit. I want them to do some dynamics. They won't tell me the answer. They say, here's it is, you can't do this, you can't do this. So I'm literally having emails with them of I give you more details so I control the dynamics and gates. They said no. So we are going back and forth, So I know their founder, Mark Raber, is an old friend of mine from MIT. I'm using my connection, but they definitely have some good technologies, don't take me wrong, and they make beautiful videos. That's all I can say.
Yeah. Well, it's inspirational, at the least, for people who work on robotics.
Well, it's a great time to do robotics, because there is success. Robotics is just a thing. It could be the next big thing, it is coming up, but it's not there yet, So this is the right time for students to do it. Because if you do gaming, okay, gaming is already mature, graphics is already mature. People can make good effects. Robotics is a field with a huge potential. You could do something really big, high impact. The chance of doing something high impact is very high. So that is why people get excited.
Yeah. Any more questions? Well, I guess it's getting late there for you, Dinesh.
Well, it's always fun to talk. As I said, I'm amazed. Beijing University has strong AI groups. I have a lot of collaborators, a lot of students from Beijing University. So it's a top university in China. And talking with smart people is always a fun and learning experience.
Plan your first international trip.
I would love to. I haven't been to China. I used to go to China so many times. I've not been there for almost 2 years now. So let's hope COVID goes away, quarantine goes away. I'll come right away again. Thank you.
All right. Yeah. Well, looking forward. All right.
And same for you. Hopefully you can visit US again to all you guys. Thank you again. Take care. Bye.
Yes. Yeah. Well, let's thank Professor Dinesh Manocha again for the wonderful talk.
Thank you for being present. We'll be in touch. Thank you. Good morning. Yeah. Good night. Okay. Cheers. Bye-bye.
Bye-bye. Good night. Yeah. Bye-bye. We'll keep in touch.
Okay.